Welcome back to your lesson of the day. Actually, for 2 days. Lesson 66, solving polynomial equations. So, we're going to be talking about things that are usually a little bit bigger than quadratics. Maybe we got cubed, or we've got to the fourth power, quintics, and upwards. Okay, so, yeah, right. And solving them typically means we're finding the roots, we're finding the zeros, we're finding the answers. And one of the main ways we do that is factoring, and we have several different methods. We're factoring these things and finding out information about the function itself, where its zeros are located, what that looks like on its graph, etc. Imagine doing this kind of stuff without a graphing calculator, which is what the old timers used to have to do. Fermat and Descartes, and well, etc., etc. Mostly in 1600s, guys were working out everything they could figure out about a polynomial without just crunching lots and lots of numbers to graph out these things over and over again. They could know a lot about them. They can know about zeros. They can know about lowest points, highest points, and then Newton comes along and invents calculus along with Leibniz in Germany. And we're able to evaluate and solve polynomial equations with lots of different methods. You don't care about all that, but I do want to let you know that on March 30th, this day in math history, Carl Friedrich Gauss, one of the probably top, definitely in the top 10 mathematicians ever, started a math journal, and his first entry in his math journal was March 30th. Let's see what the year was on this day in math. It was 1796. 1796. And he did a 17-gon construction. You can watch one of those on Numberphile. I've done one of those with a straight edge and a set of compasses. It's pretty crazy. I posted one up over by the house a few years ago. It's crazy. How do you divide up a circle into 17 to a 17-sided object? Well, the construction is there. You can take roots, any type of root that you want to, with a straight edge instead of compasses. All right, moving on. Moving on. Hold on. Moving on. There are some of these that are easier than others. So we're going to start with the training wheels on, and start with a little bit of factoring and graphing to do the job here. You're probably still wondering what in the world it is that we're going to be doing. We're going to be solving for x. That's what we're going to be doing. Duh. So on this one, say it's an easy one, what we can do is we're going to use a little bit of factoring. And you can see that each of these terms over here in this polynomial, this trinomial, which has a fourth root, fourth power thing, should have 4 answers in it. Everything has got an x squared, and everything's divisible by 2. So I'm going to factor out 2x squared out of all these and be left with x squared minus 5x minus 36 equals 0. Going to keep going because now I've got a quadratic that I can probably factor. I'm looking for the factors of 36. Negative 36, that would sum to negative 5. Can you think of them? We should. In Algebra 2. So we've got negative 36. We got negative 9, positive 4, or positive 9, negative 4. But we got negative 9, positive 4 would be the two that work. That's as much factoring as we can do, because now we're going to use the zero product property, the ZPP. ZPP comes in here and tells us that any of these factors could equal 0. If any of these factors equal 0, we've found a root. So we say 2x squared could equal 0 and make this whole expression equal 0, and x minus 9 as long as it equals 0. So we're looking for what x equals here, and we can see that obviously x equals 0. And it's x squared, so really I'm going to say it equals 0 twice. We'll get to that here in a bit. It could also equal 9, or it could equal -4. So here are our answers: 0, 9, -4. That one wasn't too bad, involved a little bit of factoring and the zero product property. Now, interesting question would be, what does that look like on my calculator? If I graphed this one, would I be able to see some of these answers? And the answer is yes. So you should probably try it on your calculator. I just plugged it into mine. And because these numbers are pretty big, the graph is going way far down and you're not seeing where it turns. But on our normal screen where we see what's going on, this is kind of what it looks like. So we get to focus on this rather than... So you got a line that comes down at -4. You got a line that comes up and then just touches the line at 0, and you got it coming back up again at 9. I can go ahead and calculate those zeros. A little bit to the left, a little bit to the right, and it'll identify, hey, no sign change, thanks a lot. But it'll identify, looks like there's 3, right? 3 places where that graph crosses the x-axis. Now I want to talk to you about how you can use that to check on these things. This one goes down, and way down, I don't even know where it turns around, and then it comes back up, and here's all I see on my picture. And then it goes way down, and then it comes back up again. So that's kind of like what my graph looks like. I can't see this, that's why I'm not putting that. But we've got a 0 here, a -4. We've got one here at 0, and we've got one here at 9. I want to talk about this one here at 0, where it only just comes and touches it. That is where we get this thing that I put on here, this multiplicity. There's actually, 0 in there twice. I could have factored this out as 2x and x minus 9 and split that up and said 2x equals 0 and x equals 0 and x minus 9 equals 0 and x plus 4 equals 0. Another important thing by I think it was, I just looked at it so I should know, René Descartes was coming up with this thing called the fundamental theorem of algebra. That sounds pretty important, right? The fundamental theorem of algebra says that if you've got something to the 4th power, you're going to have 4 roots. They may not all be real numbers. They might be complex conjugates. But no matter what, you're going to have 4 answers that will solve that equation if that thing goes to the 4th power. You can see some of them on the graph. You can see 1, 2, 3 of them on the graph. And you can see something like this where it goes up, touches, and turns around. That is a multiplicity of 2. That's what multiplicities of 2 look like. So let me give you another one. I want you to do this on your calculator. I give you an equation here, polynomial. 4x cubed minus 4x squared plus x equals 0. So one thing I want you to think about is how many zeros should you be able to find, and then the plan of attack. Are you going to factor it? Are you going to graph it? Are you going to look for zeros that way? I'll give you a hint. 2 of them are not whole numbers. 2 of them are fractions. But I want you to look for what it looks like on that graph. So I want you in about 5 seconds, pause this video, do it on your calculator, and then I'll have mine up and ready to go to answer what those answers are. Okay, did you try it? I'm going to suggest something that you do if you did the graph, and that would be to zoom in on right there at the middle where it does the crisscrossy stuff. There's actually a thing on your Zoom called Zoom Box, and you can make a little mini window around it, and it'll like zoom it for you in whatever way that you want to. So when I did it and I zoomed in, I got a picture like this, and I zoomed way in, okay? Let's get it to focus on this. Not very good, is it? Okay, so it looks like it crosses at 0, and then it comes down and just kisses the line at one other place. And if I do the calculate a 0 thing on my calculator, I already know what the answer is, but I'm going to do it this way anyway. Looks like it's at 0.5. Maybe you can see that, maybe you can't. Well, I don't know what about this blurriness thing. So the graph makes it look like you got zeros here and here, but this one right here is the part that it just touches the line, okay, at 1/2. And that's my indication that that should be a multiplicity of 2. So I should have that x equals 0, and that equals 1/2, and that x equals 1/2 again. If you were to do this same problem on your apps, on your Polysmalt 2, go to your polynomial root finder. This is a cubic. If I went in and I did 4x cubed and a negative 4x squared and 1x and 0. I did this in my calculator and then hit solve. It does tell me that I got 1/2 twice and 0 once. It knows. It knows. Alternate plan of attack. Do some math. Do some factoring. Everything has got an x in there, so I'm going to factor an x out. That leaves me with 4x squared minus 4x plus 1. This can be split up. Into parts here. Or can it be? Well, I already know it's 1/2 and it's 1/2, don't I? Yes, it's 2x minus 1. 2x minus 1, that's its factored form. So, zero product property says that x is 0, or 2x minus 1 is 0, or 2x minus 1 is 0. So solving for this, add 1 to both sides, divide by 2. There we get our answers. If you do it that way, you can see that this has a multiplicity of 2. It's the same answer twice. And then we get the answer 0 in there as well. Is that better? Okay, those are the easy ones. Spotting multiplicities then. You put that freaking sandwich down. Spotting multiplicities, a good way to do that is to look at the graph. And let me show you kind of in sketch form what that's going to look like. Anytime, let's see, I'll do a 4th power function here. I might have something that comes, it's like this, it's coming from there, and it like comes down, it touches, and then it touches again. And I only have like 2 answers. This right here is 4th power, so really you get multiplicity of 2 there, and you get a multiplicity of 2 there, where it just comes down, touches. Think about if this picture just got dropped just a little bit, and that axis was a little bit higher. Let's say that it was just 0.5 higher. Now you can see that you're going to have 1, 2, 3, 4. So if I lift this function until that is the only point, it's like those 2 zeros are getting closer and closer to each other until they're the same exact thing. This is kind of the way that they think about these things in calculus. This would be like the squeeze theorem kind of thing, where you like come in on something from both sides. So that's what a multiplicity of 2 would look like if it just comes down and it just touches the line and then turns around and goes back. I think about like the straight parts. You got like 1, and then you got a turn, you got 2, and then it turns again, you got 3, and it turns again, you got 4. Must have been a 4th power type of thing. Another picture would be something like this. We got coming in, and it touches at one place, disappears, and then it comes back, and it does something like that. This would be a multiplicity of 2 or of 4, an even number for sure. If you get a picture like this right here, this is probably a multiplicity of 3 or 5. Multiplicity of 1 would just look like that. But a multiplicity of a higher odd power, like a 3 or 5, is going to look like this. Now, it might stretch out and do one of these. Then definitely you can see 1, 2, 3 separate zeros. But if it just kind of wiggles through, it turns and then turns back, that's probably a multiplicity of 3. So look for those kinds of things. 5, it could have gone, 1, 2, 3, 4, 5 before it carries on. That's why it's a really good idea to kind of zoom in on these zeros and give them a much closer inspection. Okay, so for instance, you could try the graph 4x, or x to the fourth minus 2x squared plus 1 equals 0. It's kind of a quadratic in disguise, because when you do the factoring on this one, it breaks down to x squared minus 1 times x squared minus 1. And both of these are the difference of two squares. So really it goes x minus 1, x plus 1, and then that one more time. So you can see you got a multiplicity here. X would equal 1 twice. And you've got x plus 1 in there. That would be negative 1 with a multiplicity of 2. You got 4 roots. It's just you only see 2 numbers because 2 of them happened twice. You should check out what the graph on that one looks like. Okay, I'm going to clear the board, and then we're going to do a little bit of synthetic division, one of your favorite things to do. Let's focus, right? Let's focus. Okay, I think you should probably, in about 5 seconds, hit pause so you can write all this stuff down. Alrighty then. Hopefully you wrote that stuff down. If you didn't, that was silly because I just told you to. Alright, so synthetic division, look at the graph and see if you can spot a 0. That would be the first step. Second step, check if it's a factor or 0 by doing synthetic substitution, synthetic division, see if you get a remainder of 0. And then thirdly, now that you know that one of those things is a factor, you look at what's left over and keep factoring or do more synthetic division. We hope that we don't have to do a whole lot, but if you look in your book at example 3a, then we'll do one of these that way. So this is 3a's equation right here, and first thing I was going to do is graph it. I got a graph that looks like this, and looking at my graph, I can see 3 places where it crosses. I'm just going to start with one of them. It looks like it crosses at 1. Okay, so I'm going to imagine that 1 is one of my zeros. Or I'm checking that if x minus 1 is a factor by consequence. So I'm going to take my coefficients and I'm going to check it and see what's left over after I do synthetic substitution here. I'm looking for a remainder of 0. That's what I'm looking for. That would tell me that x minus 1 is one of the factors. So here we go. Negative 1, negative 12. Yep, we got it. So what's left is 1x squared minus 1x minus 12. We've got x minus 1, and we've got this bit left over, x squared minus x minus 12, which at this point is easy enough to continue factoring. But it also looked on my picture like 1, 2, 3, like 4 is another factor. So I could just go and do this and see if x minus 4 is another one of my factors. And I'll just use what's left here. And I'm looking for remainder of 0, right? So I drop down that. I get 3. And lo and behold, there it is again, which leaves me with my last factor, x plus 3. So I've got x minus 1, x plus 4, and x plus 3 as my 3 factors, which means that my zeros are at 1, 4, and -3. That's exactly the same thing what it looks like here on my graph. It looks like I got 3 places, and it tends to look like those are the 3 places. Now, your book in example 3 introduces this other theorem called the Rational Root Theorem. Rational Root Theorem, really it's an analysis thing. It looks at our original problem here, and it says, what are all the possible roots for this question? Now, really, unless you're doing a whole bunch of guess and check, there were very few methods for finding them. And think these guys didn't have graphing calculators. They didn't have polysmult, and they didn't have the graphing capabilities. They had to crunch a bunch of numbers and do things by hand. And look at the patterns here. It's signs, how the signs switch in the polynomial, and end behavior, and a bunch of other things to try to determine what they could figure out about this thing and give them a head start. So I didn't look up who it was that did this, but it's one of these 1600s guys. And they came up with a little formula. And they said that every rational root, that is p of x equals 0, like do the substitution and you get a 0, remainder 0, could be written in the form p over q. P is the factor of the constant term, q is the leading coefficient. So that it would be like this, like q is up here and p is down there. This one, p was 12 and q was 1. And they pull those numbers apart into all their factors, plus and minus, and list them all, and then compile a list of all then the possible answers that they could get. So 12, well, that's 1 and 12, so you can have plus or minus 1, you can have plus or minus 12. It's also 2 times 6, and it's also 3 and 4. And then you got plus or minus 1. So you got plus or minus 1, plus or minus 12, plus or minus 2, plus or minus 6, plus or minus 3, plus or minus 4 as all the potential answers or roots to that problem. Now we already found them, right? And 3 and 4, or -3, 4, and 1 were all in there. This lists all the possible ones for them to check. So you're thinking, like, how's that narrow it down? There's still 1, 2, 3, 4, 5. There's still 16 things to check on there. 16 is a lot more than infinity, or a lot less than infinity, right? So it really narrowed things down for them. And they could do some quick synthetic division to double check on those things and go after the answers better. They can also look for sign switches in this that would tell me how many and if they're positives or if they're negatives, so they could even narrow it down even further from that. If you take pre-calc, we'll go into some of that in the details, but the math's not really hard. It's just how do they figure that out? They're using synthetic division. They're using some shortcuts. They're trying to save themselves some time. So I think you guys can understand some of that. I'm not really going to make you do a whole lot of that kind of stuff. That's going to come up later in the pre-calc course as we're analyzing functions. I think you're just going to use the different tools that you have at your disposal. You got the polysmult, you've got the graphing capabilities, you can do synthetic division, and you know how to factor. That should be enough for you to figure out these things. But the remainder theorem, synthetic division, now we can apply that tool to this specific type of problem in a strategic way to give us at least a head start for how to solve these problems and to break them down into smaller pieces. That's it for that. Make sure you check your email for the problems you have to do. Also, we scheduled some math chats this week. I'd love you to check in with me. Be happy to discuss the math stuff by video call. You should take advantage of that. If you're not getting work in because you're not getting your questions answered and you haven't checked in with me, then shame on you. I'm available for as much time as you need on those days that we scheduled it. And yeah, I'd love to do that while I'm here rather than when I'm at home because I have a family that needs me. At least I think they do. I need them. So I need to be a dad at some point. And anyway, if you can check in during during the regular day between 9 and 3, that would be very helpful because I really want to answer your questions and I want to help you out. Okay, again, check your email, get those questions done. I'll send you things this week that'll help you stay on track. But you do your part to get your work done. Thanks.